summation, make it as a,
Like as a summation, exactly. So that I can break this down into log 2 PM1 plus log 2 PM2. If that's true, then I can separate, I can distribute this over these, and I have two separate sums. So now h of M1, M2 is equal to, okay, first I'll take this times that, negative sum PM1, PM2 times log 2 PM1 plus, minus sum PM1, PM2 log 2 PM2. Okay, remember this sum is over all M1 and M2. So what I can do now is I can break this sum up into terms over M1 and terms over M2. Up here, PM2 is the only term in M2, so I can take that out. So sum over M2, PM2, sum over M1, PM1, log 2 PM1, minus sum over M1, PM1, sum over M2, PM2, log 2, PM2. In the lower sum, this is the only term in PM1, so I can take that out. Now, what is this equal to? It's entropy of M1. Exactly. What is this equal to? Entropy of M2. So that's a constant with respect to M2. The entropy of M1 is a constant with respect to M2. So if I sum over the probability of M2 times a constant, this sum turns out to be 1. That just turns out to be 1. Again, that's a constant times the sum over all possible messages of M1. That sum is also equal to 1. So what I end up with is that h of M1 and M2 is equal to h of M1 plus h of M2. So what does that mean? That means if M1 and M2 are independent, remember this is the average length of the most possible compact representation of M1 and M2 together. But this is telling me, well, that's equal to the most compact representation of M1 separately plus the most compact representation of M2 separately. So in other words, if they're independent, then encode separately. In other words, there's no gain to be had by encoding them, by trying to encode them together. And that makes sense. If M1 isn't telling you anything about M2, there's no reason why you should be able to gain by knowing one or the other. On the other hand, we can have conditional entropy. So the conditional entropy, which is written this way, let's say I have message sets M1 and M2 again. The entropy of M2 given M1. This is interpreted as the most compact possible representation of M2, given that I already know what M1 is. So in other words, someone is telling me, someone is talking in my ear and telling me what M1 is. And based on that side knowledge, I'm going to construct a compact representation of M2, always knowing what M1 is. this is given by sum over all possible M1 and M2. Okay, so you might be tempted to think that it's given by this. In other words, given the same, when I did joint entropy, I substituted the individual entropies with the joint entropy. So it make intuitive sense that we would also substitute the joint entropies in here. But actually what we're doing is we're taking the average, so this is okay, this part is okay, but we're taking the average over this. And this is the average length. This is the average length. Remember, let me back up a second. The optimal length of any code word is log base 2 of 1 over the probability. The probability here is P M2 given M1. So this is the correct average length. But what I'm doing is I'm taking the average over that, and this is a function of both M2 and M1. So therefore this has to be the joint probability of over M2 and M1. So this makes sense if you think of this term, this part of the term, as taking the average, and this part as the self-information. Because this is a function of the random variables M1 and M2, so you have to take the sum over, the joint probability of M1 and M2 in order to take the average. Okay, so there's a nice property here. I will let you prove this on your own, which is the following. The joint probability, or excuse me, the joint entropy HM1, M2 is equal to the conditional probability HM2 given M1 plus HM1. And that is the same as the conditional entropy M1 given M2 plus HM2. Again, I'll let you prove that on your own, but this is called the chain rule for entropy. So let's think back to a second ago when I talked about independent random variables. So I said that, let me write this up here. If M1 and M2 are independent, then the joint entropy between M1 and M2 is equal to HM1 plus HM2. So given this and this, can we make any statements about conditional entropy if two message sets are independent? So for instance, if M2 and M1 are independent, what is the conditional entropy? This one, let's say.
M2.
It's just H of M2. So in other words, by looking at this and these, I can argue if M1 and M2 are independent, then it follows that H of M1 given M2 is equal to H of M1, and H of M2 given M1